Welcome everyone to Conversations About, and today we will talk about a problem of rock avalanches on glaciers. As I say, in these sections we will talk about particular science problems, science projects, and this one about effects of rock avalanches on glaciers, on the behavior in the moraine formation or deposits. So if you're not a really much geologist and you're not familiar with particular terms, I will try to, in this video, talked about this in a very simple way, explain why it's important, and I will base on this published paper in Geomorphology, which I am one of the authors. So let's talk about that. So this paper was published in Geomorphology and it's come out in 2011, so almost 10 years ago. And the main research I did on this paper, started from 2008, 9 and 10 basically. And this paper was one of the parts of my thesis of effect of rock avalanches on glaciers. So before we continue, you of course can find this paper online and you can download it. And I think if you're not a member of university or something like that, particular library, you have to pay for it. Otherwise, you can still read the abstract and look through the pictures, nevertheless, and see the citations. Of course, in the scientific world, we work like that. If you email somebody to some scientist and ask for his paper, they're always friendly. I've been many times asked to send, the paper. So please feel free to contact me if you want to read it. As I said here, I will explain in simple language. I will show you a lot of pictures from field sites, and I will show you locations on Google Earth. So sometimes it's better to see things on Google Earth, especially related to the glaciers. And I will just try to make it understandable for you why we decided to work on this problem, dedicated many years to this, and why it's important, and what has come out from that research, and what is the importance of studying this problem. So this paper is come out from interesting case study in New Zealand. This is where from started my PhD. There was a research done on particular in moraine in New Zealand, on the west coast of New Zealand, and this moraine is it's quite famous moraine, as it's deposited by old Franz Josef Glacier when it was deposited there. First I want to show you this Google Earth location of Vaihelup. Vaihelup, it's the moraine from which started my research. The idea of studying the rock avalanches on the glacier started from this problem. So if you're familiar with New Zealand, this is New Zealand, Southern Alps, and if we go towards the middle, towards the very epicenter of all events where the main glacier is located, and the Mount Cook itself is the highest point in New Zealand, we have this big feeding glacier sitting here, which called Franz Josef. If you've ever been in New Zealand, if you travel in Southern Alps, you probably visited the Franz Josef Glacier. It's one of the most accessible glaciers in the world. So we just park the car and walk towards its termini, and it's fantastic, it's beautiful. It's one of the glaciers which terminates into the rainforest, basically. Something which is not available around the world, only in New Zealand. There's actually two glaciers, Franz Josef and Fox Glacier, which is so close and terminated towards the west. But the Franz Josef, you can see this is its feeding area. So our accumulations area with snow falling, accumulated ice, you can see the ice cracking on the way down, flowing down through the rocks down towards. And today's position, this picture is collected in 2019 in September. So you see this position for September last year. But if we're looking down, so it was further down back in the day. And there's a numerous kind of remnants which we can go and have a look and date and find out when the last time glacier was there, even in the human history. So this, you can see this nice, like a little arch here. This is we called moraine. If you go there and have a look, there's a little cuts through this moraine. You can see there's all the glacial typical material which deposited by the glacier. So there's no question it's been deposited by this Franz Josef Glacier. And we know the dates, it's about 11,000 years old, or you can say 12. This depends how you date it. So about 12,000 years old. So the last time the glacier was here at that time. And what's interesting, what is so curious about this moraine, it's deposited this quite thick layer of material. And some research been done on this material, and instead of showing very typical classical deposited this material which is being left by the glacier deposited, we found that this material have a lot of rock avalanche component in it, rock avalanche material. It was before I started studying this, there was a suggestion that the big avalanche fall down on the ice when the glacier was somewhere here, and then it was brought down by the ice and deposited, and it helped to form this moraine, and then the glacier went back, and since then it's been melting away. When I come and start study these studies, I need to find out how important these events in the history of the glaciers in terms of how it's affecting the behavior. So maybe the glacier was going up the valley, melting, and then we have this big event, and it might cause this glacier, instead of continue melting away because of the climate, it can start growing down or just building moraine which otherwise won't be there. Because you see the glacier, since it's been retreating all these other 1,000 years, we didn't have much marked position of the glacier. So usually we build significant moraine when the glacier stay in that place for some time, and you need good cooling event for that. So a lot of glaciologists, they're just walking around the glacier's valleys, and they look for these moraines where the glaciers stay for some time, last time, like here in this case. Or we have the deposits here, here, and so on. So these moraines are very, very crucial in terms of understand paleoclimate and the behavior of the glaciers in the past. We use it right now to predict what's going to happen with the future, and we need to be sure that what we're trying to interpret will be correct. Yeah? So that was the idea, and since then my studies started all around Southern Alps, and it's include a lot of laboratory studies and studies of already deposited moraines on the glaciers, how they affect the mass balance or behavior of the glaciers. So let's come back to the paper. So the paper started with this problem, and here I'm not going to go through the paper as such, but just use it as a reference for my talk today. So we just briefly explain what is the rock avalanches on the glaciers, why it's important to study. So this picture of historical event which you've been studying. Historically, we know, as I explained, moraines are used to, as I said here, indicate the last position of the ice. And traditionally, it's referred to cooling event, or at least stays cooler event. So there was not increase of the temperature to cause the glacier go up the valley and melt away. So you need some time to, for example, to stay this glacier here. This is the Milo Glacier as well in Southern Alps. So it stays there for some significant time. And you see there's different little moraines being deposited later on. So the glaciers stay here for several thousands of years to build up this thick moraine. You just keep dumping rock by rock, creating these big moraines. But the story about rock avalanches on the glacier wasn't firstly discovered in our research. It's been known before, but it wasn't as important, attributed to be important in science as since we kind of start triggering this idea and publishing papers about that. So people describe some events, and one of the first recorded and famous event was back in 1717 in, of course, European Alps in Italy. There's a big rock avalanche fall down on the glacier ice, and you can see this picture here. This is the looking down the valley. So the rock avalanche, the glacier is up there. So if you're standing, this picture down, standing here on these moraines, I was looking up onto the ice and I photographed it, so you can see some ice there and up. It's melting away. These European glaciers are quite melting away up today. It's also a little bit covered here with a lot of rocks, so you don't see much. It's clear ice. There's a bedrock, and then you can see the leftovers of the melted away glacier. But if you looked here, this is all boulders and moraines formed. Big boulders here, where the forest actually growing on. This is all a remnants of this rock avalanche which fell down in 1717. For the moment of deposition, I think it's indicated here in purple, there was the ice was here, and the rock avalanche fell down on top of it and where the yellow lines. So it's fall down about 8 kilometers down the valley. So rock avalanche run down through the glacier down the valley. And this is the good example of picture show you that we're talking specifically not just any landslides, we're talking here about rock avalanche. And rock avalanche, I will make a separate video about that. It's a very distinctive event. So it's mean we're talking about volume. So the big piece, for example, big of solid rocks from the slope will collapse down. It's categorized to be rock avalanche. Say he should travel very big drop down vertically and horizontally. And because it's the big volume of the rock which fall down at the same time, because many landslides, they have different types of creeping down through the years, through the hundred of years. They can slide down as a mud kind of chunk. But the rock avalanche, it's actually when piece of solid bedrock just fall down, crushed into the pieces. Why it's falling down, which happen in seconds up to a minute. And then it's pulverized into very fine material, creating big boulders and fine materials all together. It will fall down and slide down a long distance. And we know rock avalanches which travel at up to 20 kilometers. Average they travel, depends on topography, up to 10 kilometers or so. So this rock avalanche traveled at least more than 8 kilometers. And can imagine why it was traveling, it started behave as a liquid, so it started flowing over the surface. Why it started behaving this, there's a lot of rock mechanics involved, so there's a lot of pulverizing and crushing material happen within. And why it's happening, there's a lot of heat involved, there's a friction with the underlying material. And in this case, it slides through the raw glacier, so this purple kind of area will be about here, where this bouldery ridges. And the ice was there, if you imagine, in 1717. So the rock avalanche fall down, slide through the ice. Also traveling through the ice, there's a lot of melting going on, a lot of, glaciers are very nice to slide down. And they always take preferable passages through the mountains. That's why rock avalanches very often fall down the valley. And if there's a valley occupied by the glaciers, they will use the glacier as a runway, as a passage down. So it slide down and then speed up a little bit, go up the hill in opposite direction and continue sliding down. So all that area where the pine trees are nicely growing, this is all deposits of rock avalanche. And if you walk through this bush, which you do because you can drive here, you can walk here quite a lot to look on the deposits, there's a lot of huge boulders which representation of a huge event. And there's a thick layer of material, several meters thick, which fall down here. If being recorded back in the day, then that glacier actually re-advanced. So the glacier was melting that time, because people already start studying, and we have these researchers who talked about this, Saussure, I don't know how to pronounce, and Agassiz. So they reported that first report Saussure, he said that the rock avalanche catastrophe caused the advance of this glacier. So the glacier was kind of melting away up the valley, and then this rock avalanche fall down, and the ice started a little bit pushing forward. And Agassiz suggested that it's happening, and partially because reduced ablation from the rock avalanche. So rock avalanche like a blanket covered our ice and stopped its melting, and the glacier need to a little bit, to find this balance between ablation and accumulation that we talked in previous video, and I described it very well. Glacier need to maintain the balance, so it's not a little bit growing because you have this constant ice coming from the top, and then when it's reached the balance, it starts retreating back. So we see these things all over the planet. So if you look on Google Earth, and I spend a lot of time hunting for rock avalanches on the glaciers, looking through old pictures, looking through moraines, looking through these interesting loops which formed on top of the glaciers. And this is all rock avalanches, rock avalanches, rock avalanches. The question is how big they are. This is another glacier with a rock avalanche on top. There's the Buckskin Glacier, there's a 2-1 event, and the second loop, second event, and you see this like a little platform formed. So this it's not actually just the thickness of the deposit. This is already several years after. You see this fresh snow on top of it, and this rock avalanche fall down, and the ice under the debris stopped melting, or it stopped melting slower than the ice around it, and it's built up this little platform of the ice. Same, this is the Furman Glacier, one of my co-writer of this paper, supervisor back in 60s, 70s. He wrote his thesis on this rock avalanche. It's in Alaska. There's another Alaskan glaciers here, and we know these events, some of them attributed to earthquakes, and they caused rock avalanche, fall down the glacier, and glacier bringing down the valley. Similar here, and of course here. This is the Furman Glacier, the one I was talking about, and we mentioned it in the paper as example. So that's the glacier just photographed before avalanche happened during the 1964 famous earthquake, Good Friday earthquake, which was dramatic, and it's caused a lot of rock avalanches and several rock avalanches falling down on the glacier. Only on this Furman Glacier we can see it's just a before event, and after you can see this big rock avalanche fall down on the ice. From here you see the source very nicely, so if you compare the pictures, yeah, that's just before and after. And there's a smaller rock avalanche, or maybe even just a rock fall, but you see it's flow down, so I'm not sure how big it is, but it's slow down, it fall down here. Only in several years, so the ice will keep flowing, doesn't matter what it's on top of it. And this is our terminus of the glacier, so, and as a result was pushing down, and it's moved this material. You can see the lines, how the ice kind of pushing forward. And of course we know that the flow of the glacier, so here if you look on the ice flows higher towards the middle of the glacier and towards closer to the Ablation Zone, and the more you're going here, they're a little bit slowing down this speed, and also it's slowing down to the sides. So as a result, when you start, this is a fresh material just deposited. When several years after, you can see this crack through, pushing material in places. So here in the middle a little bit faster, in the middle a little bit up at the valley, and it's slower here, and it starts squishing material together. And then eventually when the material reached the termini, the edge of the glacier, it starts falling down through. And the rivers, the water readjusted to all this situation, and it's continue washing off bit by bit all these materials. So that's how this bit, the terminus we call it, look like several years ago. So you see the vegetation, of course, occupying the rock avalanche, and that's another characteristic of these rock avalanches on the glaciers, because they're quite thick, up to several meters, 3, 4, 5 meters, and they have a lot of this material, crushed pulverized materials, as I say. And that's why vegetation likes it. It's like fresh little soil, so they start growing trees and vegetation on top of it. There's another case, is Hopkins Glacier in 2012, just quite recent, already during my studies happens. Furman in 64, just in the moment of deposition. Here I just explain in this picture how it's happening. So rock avalanche happening, it's falling down the valley, and if the valley occupied by ice, more probably, if it's big event, it will reach the ice, slide down, and will continue along the glacier down the valley. And exactly what we see. So the rock avalanche was coming from here, a little bit reach the wall, and then find the passage down the valley, because that's where the ice is flowing down, and it's nice and leveled, and it's easy to slide over the ice. It's like going into the river. That's another example. I'm just showing you several examples so you have kind of idea of these rock avalanches on the glaciers. That one, I believe, happened 2007 or 8, and it was one of the Icelandic glaciers. So you see, this is just a normal rocks on top of the glacier, which usually will have this middle line. This middle line fed by these two ice flows, that main ice flow and a little smaller ice flow. And in the middle you have a lot of these kind of rocks closer to the sides of the glacier, and as a result they keep supplying this and creating this line. Medial moraine, we call it. Same like you can see on the edges, we have a little bit more deposit falling down stuff from the sides. But then you have this fresh event, this rock avalanche fall down, all the way, slide down, deposited everything on the ice. You can see how some boulders are huge, And that's the picture already with the researchers. So there's a researcher standing here, he's about 2 meters high, of course. And you can see there's some ice, this is deposit on top. So the edge is a little bit, you see the material falling down with the movement, with constant melting happening from season to season. And this showing the surface of the glacier in March 2007, so that's where the deposition happened. And this is just July like about several months later. Researchers came here in the summer season, and it doesn't mean that the ice grew, so it's not like ice grow. It's mean the ice used to be here, this level, and then this ice melted down, but this ice didn't. And that's a lot of suggestion and ideas that this thick blanket of rock avalanche protecting the ice from melting. And that's where my research come from. So let's talk about specific the paper problem. I decided to look on some rock avalanches which are already sitting on the glaciers, and here in our New Zealand settings. So this is just a good quality of satellite image. You can see this is the Mount Cook area here, and we have on other side there's a beautiful Hooker Glacier coming down, and both of these glaciers in a Tasman feeding by two big large lobes here, and the Hochstetter ice flow coming from the Grand Plateau. This is the Grand Plateau where we have a hut with there's a hut somewhere there, and where usually people go on the helicopters if you're tourists or climbers. And this picture is actually a 2013 picture, because there's a rock avalanche smaller event fall down from almost the same area when before in 1991 there's a big rock avalanche fall down from Mount Cook. So just basically Mount Cook become lower a couple of meters. It's fall down, and it's fall down through the Hochstetter and here. And it's hard to tell because Tasman is characteristically covered with the debris. You see it's covered with the debris, but you can see these patches of little lakes. So this material is kind of getting thicker towards the end, but it's not as thick. Barely 1-2 meters in places. But we have this rock avalanche material that's fall down, and of course Hochstetter bring the new ice, but keep pushing this older rock avalanche material, and you can see it very nicely here and here. You see this layer here. So this is all thick rock avalanche, Mount Cook rock avalanche of 1991, pushed down. I'll show you pictures a little bit earlier ones. And this is already fresher one, smaller event that happened in January 2013. We actually done research. It's another paper. We did some research on it when it was covered by snow. And this is another glacier, and they have smaller, you see like a smaller little rockfall, kind of more rock avalanche rockfall here, which is why we went there and we measure it, see how thick it is, how it's protecting the ice from melting. Here's another more recent pictures of this Mount Cook rock avalanches. So we're looking down the valley this time. That's the Tasman Lake, the Tasman Glacier Lake. So that's the last position where the ice was sitting there for a couple thousand years. And then glacier was just kind of melting down. That's the way these glaciers behave, because they're bounded by big outwash gravels at the back. So they were sitting there for a long time, and the lake started forming, and eventually, we know that the lake is calving very rapidly. So the glacier calved down into the lake, up the valley. And even since I've been in New Zealand, it's been moved up quite a lot, several kilometers. There's a lateral moraine you can drive or walk till, well, I think you can drive till somewhere there, and then you can walk further up here, and then it's how climbers go onto plateau through this area, they go climb somewhere there. But what we did, we went down here and we walk on this rock avalanche. So you can see this like a big ridge formed. This is Hochstetter from here, and it's fall down, and you see this is all fresher ice. They've been moved in this last 20 years, 30 years, and they've been pushed down, and this is the ages of these remnants of rock avalanche. But here the material further down, it doesn't move very fast. That's why we have this lake formed. This ice is mostly kind of stagnant. There's this little feed from this ball glacier, but there's not much feeding, just a little bit to the side. So that's why this age doesn't moving very fast recently, but this part is quite active. And it's the same picture but looking from south. So we're looking now from north. This is looking from south. This is actually I'm standing on lateral, and I'm looking down. So this is the Mount Cook rock avalanche. You see a very distinctive, nice straight line. And then further up, you see there's already kind of more normal-ish debris-covered ice. It's a little bit tricky with New Zealand glaciers here because they cover it with a lot of debris, but you can see the difference. This is the superglacial material on the ice, which formed mostly from melting down. So the ice was thicker. You see the lines where the ice used to be before here, here, here. So the ice was like that, and it was probably more quite clear at that time, and then it started melting down during the last couple thousand years. And wherever rocks within the ice, and there'll be always rocks within the ice, because while the glacier traveled down the valley, it's accumulating a lot of rocks. These rocks will be exhumed towards the surface. If you have a chunk of ice and something within the ice, when the ice all melted, will be left on the table. There will be left just whatever bits was within the ice, flowers or whatever you put into your ice. So same with the rocks, and that's why we have a lot of glaciers, especially if you look all around Himalaya and so on. There's a lot of rocks on top of them, but they're not very thick layers, so it's a lot of nice sorted material, kind of angular stuff, angular rocks. And then we have this rock avalanche material, which I told you before, composed this all different thickness rocks. In the bigger, you see the huge boulders. These guys definitely fall down from Mount Cook rock avalanche. And we have a lot of fine pulverized material. And even when we were doing research already here, there's already some vegetation started growing, where you don't have for 1,000 years vegetation anywhere on this normal superglacial material. There's not enough material to grow vegetation, not enough fines. This is just a picture of the smaller rock avalanche that fall down on a ground plateau. It's not as big, but you can see how it nicely flows well. And that's the picture of the second one. This is the type of carapace, big crushed rocks on the surface, which we usually find on this type of the events. So this is just showing what we did. We went to the field and we decided that this is Hofstetter here. We decided to kind of survey through the deposit to see through the boulders down through the ice. And we did the same on the Mount Cook rock avalanche. And we used grain penetrating radar. So grain penetrating radar, it's used by geophysicists to study what's happened down into the earth, what type of different layers of the earth you have. You can measure for several meters down into the ground. And that's what we did here. Of course, you can understand, to get there, ground penetrating radar, we need to have a helicopter flight. This involved huge machinery, huge antennas, which are very heavy, 2 antennas, 1 person for each, and huge and heavy batteries for these guys, because what they do, they give a signal down through the earth or the substratum. In our case, it will be several meters of rock avalanche and the ice beneath. And when you survey, you can then interpret these wave patterns, and you can see the difference of the medium. So how dense a material, is it water, is it air there, and these kind of things. So that's what we did there. So here the picture of first results for Mount Cook. So that's the person standing on the edge of the Mount Cook rock avalanche deposit. That's how it looks on the side. So very characteristical crushed coarse material on the surface, which is our rock avalanche. So what's happening, that 1 person is measuring and 2 other person carrying the antennas in particular distance to each other, and 2 antennas, they send this electromagnetic signal down through the rocks and ice, and then we can read this at home, luckily, and interpret. So it's basically, it's work on a very, very high frequency waves, radio waves. Can you see this H? We ran it through here, and we found that the deposit, you can see we found our ice. So this is our normal, we did run it through the normal kind of glacier, superglacier material, and it's nice and easy. You can see this image here, and we ran it through rock avalanche deposit. And here we see distinct line when the rock avalanche contacting with this ice underneath, and in places it was as thick as 10 meters. And that's how deposit been already pushed by the ice and a little bit squashed together, but still originally maybe it was at least 5-6 meters. And if you have a look on some boulders, look at some guys, these boulders, they're quite thick. So even a couple boulders and you already have your 3-5 meters thickness. So it's not surprising. But it's proved the idea which we try and show here, that you have significant thickness of the deposit on top of the ice, that you have this ice underneath that reduced its ablation. Here it's a little bit, you see, pushed down and up, this ridge buildup, but it's because the way how Hofstetter pushing down this rock avalanche deposit. But in other places, like next case, we'll show you, will be very, very nicely platform sitting on top of the ice. And this just example I'm showing you, this normal superglacial. You see thin material rocks, and it's about up to meter thickness in places. Without rock avalanche material, it looks like that. It's actually quite interesting. It's when you walk on these things, it's quite dangerous. So you need to have good boots and stuff if you want to walk on it, because this material, the glacier, first of all, moving all the time. You have rocks sliding, so you have these little ponds everywhere. So you need to be very careful. Here, just showing the rock avalanche material composition. It's a very famous picture we have for representation. You have a lot of mixture of crushed and very fine material in between. And here is the example of the normal stuff on the glacier. So second picture, second deposit we study. I'm sorry, it's not the best picture here. So you can see this is the rock avalanche sitting here on top of the ice. Yep, here. And you see there's a little H. This is the ice there and the deposit on top of it. And this is the sliding slope. This is a sliding slope. This ice is melting more down with the movements down the valley. So the glacier keep moving this rock avalanche as well, and a little bit redistributed its position, so it's becoming more kind of curved down the valley because of this differential ice flow within the ice, as I told you. So the thicker and the faster flowing ice towards the middle of the valley, the slower to the sides. Kind of just the physics law, how the material will flow down the valley in a confined valley like that. And you have rock avalanche deposit on top, and we measure, although it's very small event as I show you, up to 7 meters thickness here. So we run it all the way through this guy. It was 7 meters thickness. The highest, you have a little bit structure through the ice, cracking, and of course this ice will be sitting there for last several years since the deposit fall down, and while it's moving down the valley it will be modified. So that's what I want to show you. That was the main findings of this paper, and I will just one more time revisit it. So come back to our Google Earth image. This is actual Google Earth, which you can open today, and this one is dated in 2018, so quite recent. You can see you already don't see this rock avalanche deposit here on the Grand Plateau. You can see we don't have already this nice beautiful rock avalanche deposit here. It's fall down in 2013 in January, and if we look on the modern Google Earth image, it's already not there, but it will be there, and it's already start moving down towards the Hofstede, but it's just covered with a fresh new snow. It's enough next season, and there'll be enough snow will cover down and bury it. But here down the valley, rock avalanche of Mount Cook stay here. For today, it's actually 2018 September. That's the image in the Google Earth, the more recent one we can find. Very beautiful. You can see that's how these lines have been deposit pushed down. This is more fresher, just a debris cover on the ice, you can see. And this line as well, this is the remnants of this deposit, so it's been squished and moved down, so the Hofstede basically active through here. And this ice here, mostly kind of stagnant. You see a lot of lake stuff forming, so stagnant's not stuck here for a moment. And because of the topography, it's just been trapped here by this active Hofstede. And it's also because this ice, it doesn't have enough feeding to grow as fast, you see. And it's stuck here, and this you see rich as well. These remnants, this is all as well. Mount Cook rock avalanche deposit here. And this is already this, as I said, you see very stagnant ice. Basically, there's a flow of ice a little bit here, but it's not as much here, and that's where the glacier is calving actively today. See how many icebergs is here, and the termini for the moment when the last time glacier was active. Beatrix, the smaller one, the one I showed you before, how far it's moved, that's how it's changed and moved already. It's gonna glacier a little bit, smearing it down, pushing it towards each other, so I'm so sure it's now even thicker than 7 meters. But why we need to study this, why we need to look on this thickness? In the paper, we were talking about how this rock avalanche will cover in this ablation zone, good ablation accumulation zone of the glacier. But in ablation zone, as I showed you just before, if it's fall down on accumulation zone, the next snowfall will cover this ice, and it's just the deposit will be within the ice. And then the moment it will come out to ablation zone, as I explain you how superglacial material appears on the surface, it will become eventually exhumed. So the ice will melt till the deposit, and deposit will be exposed to the same radiation. And when that happened, there could be two scenarios. First, if the material is very thin, the material, I'm talking about several centimeters, which is not happening with rock avalanches, it will start accelerate the melting. If the material is thick enough, more than several tens of centimeters, meter, and so on, and in our case you can see it's going easily up to 7-10 meters, it will protect the ice from melting. There's another paper which came out before that paper in which I do research on how debris cover protect the ice from melting in the laboratory. So I ran a lot of experience with different material, different thicknesses, different conditions, rain, no rain, so on, and see how the debris affect ablation. And come out, there's some studies been done before on top of the glaciers, people noticing if you have thin layer of the material, it will accelerate the melting. If you have thicker layer, it will stop in ablation, stop in melting of the ice underneath. And you have thick enough, and some people concluded for particular glaciers in particular elevations and climate conditions that you need about 3 meters of rock. In our case, we can say surely that yes, we diminished ablation quite a lot. And here is just a little picture showing you that this diminished ablation will cause the glacier to be moved further down the valley, that it will be without the deposit. So without the deposit, the glacier will be here, stay here in equilibrium. Yeah. With the deposit, you will protect this ice from melting. The material keep coming. The new fresh ice keep coming from up the valley, and we'll move it down, down, deposit it. And then there will be the moment when this ice starts melting down, or the glacier will disconnect with this older dead piece, and then some kind of material will be formed. Could be just a blob of material, could be nice moraine formed, and then the glacier will start moving back up again into its equilibrium. And that's what you can see on this picture. So it's just explaining that we can form some kind of material, moraine-ish type thing in front of the glacier or sides of the glacier without cooling event and climate. So you can have material deposition happening due to the rock avalanche event, or earthquake happened, rock avalanche happened, doesn't matter, earthquake triggered or not. Event happened, it's produced this material, the glacier went away nicely. You researcher, you come here several thousands or decades after the event, you date this moraine, and you think there was a climate event in this region, in this hemisphere or the planet. Not necessary. So that's whole the point of this paper. We need to be careful when we interpret climatic events and response of the glacier. That was the main point of this paper, and we come back to this Waihu loop example, and we're just roughly showing how much we need to cover the modern glacier to build it up and create this moraine. We use this to show here in this picture how much material we needed to cover ablation zone, ablation where the ice melting, so down from equilibrium line. So for the moment when the ice was about here, canvas snope, you need about 80% cover of your ablation zone to cause the glacier, instead of stay here or continue retreating, to re-advance, to move down the valley, deposited all this stuff, and then retreat. And more probably that's what happened that time. And it doesn't matter the rock avalanche happened due to earthquake or just rock avalanches just falling down with no particular reason. And we observe it right now around the world. Fall down on top of the glaciers. We have rock avalanches like in case of Alaska in 1964, when you have about 30 rock avalanches that fall down on the glaciers, Sherman included, which was attributed to the huge earthquake. So earthquake or not earthquake, in these events quite often, especially in very active zones like all around Pacific Ring of Fire, around New Zealand, Alaska, Andes, all these glaciers affected by earthquakes, and often just the glacier can start advancing from the earthquake, but because they don't have much material, so they just go down and then back up. But the rock avalanche is causing this, a lot of material, building some kind of moraine. So that's what I want to talk about. So going through the paper, so it explains about here, talking about type of material, which I talked about. And then I described the insulation mechanism, so that is how this actually diurnal cyclicity causing this material to protect the glacier like a blanket, protect the ice from melting. Field studies, ground penetrating radar survey, and we describe in this Beatrix and Mancook. You can read about the results. And then we talk about response of glaciers to positive mass balance. So this was idea also that a lot of rock avalanche bring a lot of material into the ice as well, might accelerate the ice flow movement. But in case of the Tasman Glacier, it wasn't such important. A little bit talking about how much percentage you need to cover it, just what I explained right now, in the consequences. It might form some kind of moraine, still questionable. And the very important, it's paleoclimatology, so how it's important to understand the climate in the past. And particularly, especially in that decade, there was so much spark of research around New Zealand happening, dating all these moraines and very nice dating techniques, which I will have separate talked about, which dating techniques we use to understand how old the rocks, and then how it can affect our interpretation. So we date it, and it's not the problem with the dating. So the dating could be very perfectly nicely and correct, but the problem appears when we're trying to interpret what doesn't mean. And it's in everything in science. You have particular facts, but it's up to scientists to make conclusions. And this paper showing that we need to be very careful with interpreting this type of settings like New Zealand or others like Himalaya or Alaska. We need to very be careful interpret these moraines and attributed everything to climate change. Maybe not necessary. You can read the conclusions of this paper at the end. So we're talking about the large rock avalanches can fall down the glacier and affect its behavior significantly. So this caused this premature kind of re-advance. These rock avalanches driven moraine advances can form terminal moraines. They not necessarily can have climatic association. And in my thesis, you can have a look if you become interested in all this topic I talked about. It could happen there was an climatic cooling event and rock avalanche, big moraine formed. You can have no cooling, no warming of the climate. The glacier was just staying stable, and you have this rock avalanche and it's just formed the moraine. You can have a situation where the glacier was retreating because of the warming event, and then the rock avalanche fall down, build the moraine, and then continue retreating. So there's all different type of scenarios, yeah? It says that we need to investigate further how it can form the moraine. And also the last point we talked in this paper is how it's have effect on society. So these dramatic events, falling down rock avalanches on the glaciers, they can cause destruction like loss of lives, damming areas, flooding, and so on. And then you can get familiar with the references and acknowledgements. Thank you so much for being with me throughout this paper. It was published in Geomorphology, I just remind you. And I hope you enjoyed this video about this paper in particular, but it's not just one paper, and there's a lot of papers related to this problem, and whole of my thesis as well related to that. And as well, I looked how to identify it in older moraines. I talked about a specific effect of rock avalanches on the glacier like we talked today. I also considering problems of paleoclimate reconstructions, so how we use these moraines and can we use them to understand the climate of the past and in the future, and so on. So there's so many directions you can go from that. And I hope you'll appreciate the physical demand for this type of papers which I present here, how much was involved in that work, and here with rock avalanche deposits. It's very catastrophic, very hard things to just walk on top of and study them, but they're majestic and they're amazing, and they give us so much information about formation of deposits, about how the mountains eroded, how much material moved, how it's moved, what's happening with the ice, with the glaciers, with our climate understanding, and so on. So I just hope you a little bit become familiar with all these things, and I hope my language was understandable, and I hope you enjoyed it, and I will see you in other videos about different topics in geology, geography, and other science of Earth. Thank you so much, and have a lovely day.